Okay, this is what's called a reaction profile. This is a very important concept. This is a reaction profile. This is one of the other main topic that your instructor went over in the last lecture, is these reaction profiles. On the vertical axis, we have energy. By the way, what's good? High or low energy? Yeah, low energy is good. Everything wants to lower its energy to become more stable. Low energy is better and happier. Does anyone know, and on the horizontal axis, we have something vague that's called the reaction progress. It just says how far along the reaction is. Anyone have any ideas how I should label this region of the curve?
Reactants.
Yeah, starting materials or reactants. So then how should I label this? Right. So is this reaction exothermic or endothermic? Exothermic. Label the delta H. Let's label the delta H for this reaction. Now we're trying to figure out what the delta H is, right? Now, what does delta mean?
Change.
How do we calculate the change?
Final minus initial.
Well, where's H final? Here. And where's H initial? Here. So a couple of people are wondering whether we should use this over here, but this is neither final nor initial. So just from the definition of the delta, we know that we should just be comparing this level and this level to find the delta H.
What's that question on this? Like, what did you ask?
Oh, I got it right. I know we do.
So this is the distance that's the delta. My question to you is label delta H on the graph.
Oh,
Label delta H on the graph. Which distance on the graph represents delta H? Delta H is the vertical distance between where the starting materials are and where the products are. Delta H is the vertical distance between where the starting materials are and where the products are. Yeah?
I'm confusing delta H and delta G.
Yeah.
They're the same, aren't they?
Yeah, I get them confused too. Well, they're not the same thing. I think you're going to study the difference between them more after the midterm, so I don't think your instructor is going to stress that too much right now. They're not exactly the same, but they both measure energy changes. And in many cases, they're approximately the same. So right now, we're not going to think about the difference between them. So it's true that sometimes people interpret this vertical axis as G, the Gibbs free energy, and sometimes they interpret it as H. I think the very best thing to interpret it as is G. But that's actually not what your instructor did in lecture, and that's not what the textbook is. Right now, the textbook here is just focusing on H, because in many reactions, they're approximately the same.
If I put G, do you think it's going to be considered like?
But he in class he said it was awesome for this was delta G.
Okay, because then I'm.
Yeah, so if your instructor specifically talked about that, I guess they would allow either of them. But I think what your instructor actually did is they labeled it as
H.
delta H.
But
Yeah.
but then in class he changes his notes.
Oh.
Yeah.
Yeah, all right, so in this version he had delta H, but there's also, there is an argument, maybe it would be better to call this delta G. Delta G in a way is more important. I think after the midterm,
But isn't delta H intensity?
have you guys ever seen this equation?
Yeah.
All right, I think you're going to study that more after the midterm. Well, the key thing is, in many reactions, the change in entropy is very small.
No.
Well, if the change in entropy is very small, then delta G is approximately the same as delta H. And then people get sloppy and they use them as synonyms for each other. So maybe we should just assume at this point that we're looking at reactions where the change in entropy is very small, so we're not going to be too punctilious about whether we're using delta G or delta H. I'll stick with what the textbook does and what you have in these notes, but it looks like your instructor is kind of going back and forth. So to be fair, he would have to accept either of those. Okay.
The delta S is disorders.
Yeah.
It's just entropy.
Oh, it's a
The
heat.
energy
Yeah.
and bonds when they
Delta
do
H
something.
is a heat center.
Yeah, this is a measure of energy change, and this is a measure of entropy change. And again, in many reactions, not all, but in many reactions, the entropy doesn't change very much. And in that case, this term would be close to zero, and then these are approximately the same, and therefore, oftentimes, teachers are a little bit sloppy about distinguishing between them. And it's pretty traditional when we teach reaction profiles. So I don't think you're ever going to be given a reaction profile where they're going to test the difference between delta H and delta G. There's not going to be any trick questions here where they're trying to trip you up between using the wrong delta H or delta G, because teachers are just as sloppy as everyone else here about this. Okay. So I'll stick with the delta H. You guys had said this was exothermic, and when you said it was exothermic, you weren't thinking about this. You were comparing this level and this level. So logically, this is the level that we should have their delta H. Notice that we went down, so delta H would be negative here. If you actually calculated delta H, it would be negative, because this is an exothermic reaction.
So what does that peak represent, from the starting materials up to that peak? Is that the activation energy?
Good question. That's right. So we do need to know how to label that as well. So let's label what the activation energy is here for the forward reaction. What would be the activation energy for the forward reaction? This is what you were just mentioning.
Yeah.
And so the backward reactions is the whole entire thing.
Yeah, let's talk about that in a second, actually. Now, what's the interpretation of this? So this reaction is exothermic. So does that mean that it's totally easy for it to happen? Well, no. Even though ultimately this releases energy, first it has to get over this hump. This is what's keeping this reaction from happening, all right? Ultimately, we would have a released energy, but only if we can get over this hump. So again, using the collision theory of reactions, when will this reaction happen? Well, first of all, the starting materials have to collide. Secondly, they have to collide in the right orientation, which we're not going to talk about too much. And thirdly, they have to collide with enough kinetic energy to pop themselves over this hump over here. Only if they collide with enough energy to get over this hump can they now go back down. This is kind of like trying to get over a hill, basically. If you once you get up to here, you're home free, and you'll just slide all the way down naturally. The hard part is getting over this hump in the middle. All right, and how big the hump is called the activation energy. This is how much energy it takes in order for this reaction to happen. Okay. So here's our activation energy for the forward reaction in this case. Now, there's also a reverse reaction. So let's label the activation energy for the reverse reaction.
This is the big one.
Mm-hmm. So it would go from where to where? Oh, you've already got it labeled. That's good.
So first it needs to get a little bigger.
Okay. Now, I think you guys might have started talking about this on Friday. Well, have you guys had class today? Yeah. So today you started working on equilibrium, and we already talked about this a little. All reactions actually go both forward and reverse. The reverse and the forward reactions are happening at the same time. So once we make some products, well, every once in a while the products are going to collide with each other and turn back into the starting material. So the reaction goes in both directions. Well, in order for the products to turn back into the starting materials, first they have to collide, second they have to collide in the right orientation, and lastly they have to collide with enough kinetic energy to get themselves over this hump. And then if they do, they get back to here. So this is the activation energy. I should have said this is the activation energy for the reverse reaction, and this is the activation energy for the forward. In many cases, people don't bother labeling the activation energy for the reverse reaction because it adds some confusion, but sometimes you do label it. I think your instructor talked about it, so it's important to be able to look at it. So only the activation energy involves this hump. The delta H just compares the final and the initial points. By the way, notice that delta H could be positive or negative, but activation energy is always positive because the hump is always higher than these 2 points, because if it wasn't, there wouldn't be anything to get over, in a sense. So the activation energy, this level, is going to be higher than these two. This seems to be a reaction where the equilibrium is going to favor the products, and you can see why. After a while, we'll have both starting materials and products, but whatever starting materials there are always going to find it pretty easy to get over the hump and go down here. But anytime you make the products, they're not going to find it very easy to go back. They're kind of stuck down here once they get here. So this is a reaction where the equilibrium probably lies far forward. Because this is exothermic, the equilibrium here would probably lie far in the forward direction. Once you get down to here, we're stuck. Okay. This is labeled as the starting material. This is labeled as the product. So what should I label this as?
Transition state.
Good, the transition state. Did your instructor use this symbol, a double dagger? Sometimes people use a double dagger to indicate the transition state.
No,
But maybe
Just transition.
just transition state. All right, so I'll just write it as the transition state.
How do you put it double decker?
It's kind of like this. Sometimes that's used as a symbol for the transition state, but I'll just write it out.
No, just for themselves.
All right, so, not the state of transition, but the transition states. All right, so this point here is starting materials. This point here represents products. This point represents transition state. Activation energy is the distance, is a vertical distance between 2 points. So the forward activation energy is the vertical distance between starting materials and the transition state. The reverse activation energy is the vertical distance between the products and the transition state. So here's another good way to define the activation energy. The activation energy is how much energy it takes to get up to the transition state. In the forward reaction, the activation energy is how much energy it takes to go from the starting material to the transition state. And in the reverse reaction, the activation energy is how much energy it takes to go from the products to the transition state. Whereas delta H does not involve the transition state at all. Delta H just compares the final products and the internal and the initial starting materials.